Lecture 5.5, different types of capacitors. The most common types of geometries for capacitors are parallel plates and cylindrical. To compute the capacitance of any capacitor, one uses the capacitance is equal to the charge divided by its voltage. So let's go do that. So let's start with the parallel plate. I know that we've already done the parallel plate, but this is sort of like to set the tone of how we're going to deal with the spherical and the cylindrical. So here is our parallel plate capacitor. So for parallel plates, the electric and potential fields are constant. So I should be careful. The electric field is constant, but the potential depends on distance. Using what we've already done in lecture, I imagine that I have parallel plates. So if I'm looking at these parallel plates, then I'll put my charge on these guys. Then what we're going to find here is that, of course, we have a plate separation, little d. Of course, we have an area, A right there, and then we're far away from the edges so that I have a uniform electric field. So language-wise, we typically put the lower plate at 0 volts, meaning that it's the ground. So in other words, this is the low potential. Up here is the high potential. So if we look at the E field inside, we've already shown that this guy was eta over epsilon, which is also Q over A divided by epsilon. And if I look at the voltage here, the voltage of the parallel plates is then going to be the electric field times the plate separation. So if I look at the capacitance now, the capacitance is the ratio, the capacitance ratio is that I have this guy over this voltage here. And if I substitute in the charge and the expression in terms of the potential here, we get two terms. For the charge, if I use the first expression, I'm going to get epsilon A times the electric field inside divided by D, the plate separation, times the electric field inside. And right away we can see here is that the electric field cancels out. and we end up with a characteristic equation for the parallel plate capacitor. Again, I did this very quickly because we've done this already. Now I want to show you another capacitor and apply the same technique. This is a spherical capacitor, and the only use of a spherical capacitor is that it's conceptual in nature. I am not aware of any application other than an isolated sphere, but it doesn't have two plates. So if I have a spherical capacitor, we have two concentric spheres separated by a dielectric. So let's see if I can draw these. So these are always tricky to draw for me. So let's see. So I'm going to try to do a side view where I cut this guy open. So I have this. So I'm going to say, here's my thin outer shell. Now I have my inside. And I'm going to imagine that this is just half of a sphere. And then I got to draw my other half of the sphere right here. So when I'm looking at this, this is the positive charge. Outside is I have a shell. Now, when I'm looking at how I'm seeing this, I'm seeing that this guy has a charged inner sphere. And then the blue here is the dielectric. And so when I look at the outside of this guy, I'm seeing that this guy has a negative charge all the way around. So I would call this a side view. So if I was to take this and look at the front view of this, then I would see something like this. I would have my central sphere, and now I have to draw my edges here. And that's my spherical shell. So then I'm seeing that right here is my inner plate. So this has all this charge right here. I have my outer plate, which will be in gray. And then I have my dielectric inside. Now I have the same thing as I did before. This is my high. And then I have my charges, negative charges, all the way around on the inside. And that, so if I take this and I attach this to the ground, the outer shell, then I get 0 volts. And that's why you're seeing the negative. So if that's the high in yellow, the outside shell is then the low. So then I'm going to have two radii. I'm going to have the inner one, which is A. Then I'm going to have a very thin shell, which I'll just call it B here. So that's my spherical capacitor. So to calculate the capacitance, we know what to do. The capacitance is C spherical. For a spherical capacitance, has to be charge divided by the voltage of this sphere. So for the sake of argument, I'm just going to ignore the dielectric right now. I don't have to, but here's what we're going to look at. So to get the voltage, we then say that the work slash voltage required to move a test charge from, I don't know, from the outer shell to the center is, so once again, I'm gonna come in here and I'm gonna copy this and just look at this guy right in here. So I'm gonna get rid of the dielectric because it's just gonna be easier to sort of like, just talk about what we're actually seeing here. So I need to get rid of that. So now I have this. So I'm going to pick my Gaussian. And where am I going to pick my Gaussian? I'll pick it right here on the inside. So then this tells me that the distance from there to there is R. Once again, this is my Gaussian. So to calculate the voltage, we do the exact same thing that we did before. We come up here, and I'm going to say that I have a little test charge. So I'm going to make this test charge green just to make it stand out. So I have this little positive test charge that I'm then going to move from B towards the center, which will then be A. So here I go. So my potential from A to B here, from B to A, is that first I have to start at infinity, then I go all the way to there. But because this is a capacitor, the net charge is 0. So then I look at the electric field outside, and what I'm seeing is that this guy is 0. And the reason why it's 0 here is that when I look at the enclosed charge, it's equal to the charge on the inside, and then I'm going to say minus the charge on the shell. And this combination will give us 0. So then I'm integrating from B to A, and this is the electric field of a sphere, because we enclosed all of the charge that's in that central sphere. So if I look at that, this is just the electric field of a sphere. So then I could come in here and I could write minus 4 pi epsilon. This will then be Q, and then I'm integrating from A to B of dr r squared. And so the algebra comes out like this. We get 4 pi epsilon into Q, and then my algebra gives me this. But that's not the way we want to write it. So if we rewrite this, it'll make more intuitive sense if we rewrite it so that it looks like this here. So it's going to be B minus A divided by AB. And I'm saying that this is the potential of this sphere. So then what is the capacitance? The spherical capacitance is then going to be C spherical. This will then be Q over the voltage of a sphere where I'm moving it from A to B. And then if I plug my values in here, I'm going to get Q 4 pi epsilon. And then I'm going to get the quantity B minus A divided by A times B. And that's going to be also that Q. So right away, we can see here is that these charges cancel. And so when the dust settles here, now note I've been making a mistake by putting epsilon naught here. We shouldn't be putting epsilon naught because it could be the general term is to make that epsilon. So if I clear this up here, I'm going to get this is epsilon times the quantity 4 pi AB divided by B minus A. And so this guy is the capacitance of a sphere, a spherical capacitance. So note that this is the exact same form, right? This has the capacitor characteristics. And what I mean by that is that when I look at the capacitance, it should be the type of material, and it should be times the geometry of the spherical here. And so then I'm going to get epsilon, and I'm going to get 4 pi AB over B minus A. So when you look at these details, what am I seeing here? This right here, this is the plate separation. On the other hand, this guy right here is the average geometric area between the spheres. That's amazing. So what I want you to think about here is that in the beginning, I mentioned this, but let me say this again. There are no device that I'm aware of that uses a spherical capacitor. So the way they make an application is that they say that maybe on the other hand, one can consider a single sphere capacitor, and a lot of time they call it an isolated capacitor, where the second outer shell is grounded to Earth. In other words, they have the blessing to say at infinity. For electronics, this has no practical value that I'm aware of. So for electronics, oops, this is of no practical value. And what that really means here is that it's mainly used as a concept for understanding. So one example would be the Van de Graaff. So we could say that the Van de Graaff is an isolated capacitor, spherical capacitor. And the way we look at it is we look at it this way. So we have a sphere, and we have now charged this sphere. And let's say we have charged it with a positive charge. And then, of course, I have my stand that's connected to the ground. But this really doesn't play very much of relevance in this. So what you're seeing here is that now I could imagine that this is A, and then I have a second shell. And the second shell could be at infinity. And so when I'm looking at this guy right here, you're seeing that this distance to the inside is then going to be B. The rest of this is my dielectric in between. So because these guys are conductors, we have to induce a negative charge right here. So in this situation, we're going to say that that's our permittivity. So now if I look at this limit as B gets much, much bigger than A, and the idea here is to set R equals to infinity for the second shell. So if I take the limit of this spherical capacitor, I'm going to get a value where I'm going to get, so if I now factor out a B term, then I'm going to get something that reads something like this. It's going to be epsilon times 4 pi A 1 minus A over B, which in this limit where B is much, much bigger than A, then I'm going to get 4 pi epsilon A. And this is what we call an isolated spherical capacitor. So then the last capacitor that we want to talk about is that we want to talk about cylindrical capacitors. So let's go look at that. Now, a coaxial which is typically used for transmission of radio frequencies, looks something like this. And we'll go through the details. So a coaxial cable is used as a transmission line for radios or radio frequencies. So when you're looking at this, here's what you're seeing. This you'll see that there's pieces. There's the inner conductor. That inner conductor is what we would call the inner copper cylinder. And then you have two pieces to the outer. This is the outer cylinder. Also acts as a Faraday cage. So we could go in and we could calculate this capacitance. So to calculate the capacitance, right? To calculate capacitance of this cylinder, again, we use, in this case, C equals to Q divided by delta V, of course, the cylinder. So let's go calculate this. So the Gaussian of a charged cylinder is like this. I'm going to have a rod, and the only thing I know here is that according to what we've been talking about, if this is isolated, that means it's all acting by itself. So then I have charge all symmetrically involved in this guy. So now I'm going to choose my Gaussian. So if I choose my Gaussian, one of the things that we said here is that we're not at the endpoint. Okay, so there's my Gaussian. So when I look at this thing, we could see here is that I have a flux. And I have my area vector going like this. They're pointed in the same direction. So that's just the field of a wire. So I could then say that this is the field of a cylinder. And for a wire, this is then going to be A divided by lambda for A. Let's see, so I got to be in between the two shells here. So it's going to be for A less than or less than B. So now I could go calculate the potential field using Gaussian's method. So calculating the potential field is then going to be like this. So I have my system. Let's just bring this guy. So if I bring this guy down, I have this field that I'm going to integrate over. So what do I know? I have this right now. So I'm going to move my charge. So I know that this guy has a radius of B from there to here. And I write an A. Just call that B. And then what I'm going to do here is that I'm going to bring my test charge. I'm going to come in here with my test charge and I'm going to move it towards that charge right there. So as I do here, then my voltage from A to B here will then be minus BA, the E field of a cylinder, dr. But if I look at this here, this is just a wire. So this is minus 2 pi epsilon naught lambda. And this will then be dr over r, which is AB. Now, you might recognize that this guy here is a log, a natural log function. So then if I integrate this guy, I'm going to get 2 pi epsilon into lambda, and then I'm going to get the natural log of b to a. Now I know that lambda is also q times L, so if I rewrite this, what I'm really finding is that I get a value that then reads 2 pi epsilon divided into q times L, and it's the natural log of b divided by a. And this is the potential or the voltage for the cylinder. So now I have my field here. So now let's go calculate the capacitance. So the cylindrical capacitance comes from the same equation. So then I'm going to say C cylinder is then going to be charge divided by the voltage of the cylinder, which will then be, I have epsilon, the material, I have 2 pi L divided into the natural log of B over A. And this is the capacitance of a cylinder. So we have calculated the capacitance for 3 different things. So what I said here is that the capacitance for a spherical capacitor is conceptual in nature and doesn't exist. So the only thing we really want to talk about is parallel plates and capacitance here. So here we go. So now we have, let's talk about parallel plates. Let me be more careful. We should say, what are the differences between a parallel plate versus a cylindrical cap? So what do we know? Well, let's start with parallel plates. So if I look at parallel plate capacitor, what do I see here? They're generally very small. So what do I mean by small? That means they're typically on a range of about 1/8 of an inch to about 1/2 of an inch. So it's not very big. So they're very small physically as well as capacitance-wise. So they're generally flattened with 2 wires. So if I look at them, here's some images that I found on the web, and they come in different types. We typically, in the lab, we typically see ceramic, aluminum. We do have some mylar, but typically you're going to see, if you see any of them, you're probably going to see either the ceramic or the mylar capacitors. So when you look at this thing here, what you're seeing here is that what this means when we talk about a capacitor that has mylar, that just means that mylar caps use mylar as the plate separator. In other words, the dielectric. So in these capacitors, they're typically really, really small. They have capacitance of a range typically in picofarads, nano farads, and that's what we find in there. And what you find here is that they're used heavily in analog circuits. So I would say sort of like applications are analog circuits where they use them quite a bit. Now, there's another type of capacitor, and these are the ones that I typically have in my circuits class when I teach it. We have cylindrical capacitors. And cylindrical capacitors are really, I would say that these are, for lack of a better word here, bread and butter for ordinary applications. You open up any type of electronics and you're going to see the radial capacitors. And the reason why here is that they achieve a wide range of values. You can go to, just shy of a microfarad to thousands and thousands of microfarads. So the two common ones, you know what? I didn't spell common correctly. The two common ones are what they call axial. And you'll know axial because they have the leads are coming out of either end of the cap. And the second one is the radial. So what's distinct about the radial one is they have both leads come out of one end. And so we use both of these in physics here. So you would see these kinds of ones like right here. So you could see here is that the first three, all the way from paper to bipolar here, those are axial capacitors. The electrolytic ones, which is what we use a lot in circuits, actually does this. Now, what I want to show you here is that it's really easy to burn out these capacitors, cause dielectric breakdown. And in the lab, it happens, well, it can happen a lot. So what I want to do is that I want to show you a video. This is linked, and this guy, he's pretty interesting. So the name of the video is Bust the Cap. So let me go share my screen, and then let's go play the video here.
Hi, I'm Sean with SparkFun, and today we're going to blow up some capacitors. So we have three different types that you would normally see on your circuit boards that you might be using. You have a basic ceramic, an electrolytic, and a tantalum. And these vary in order from good to evil. They have different properties, and as you can see, they come in various different sizes. And they have different uses for what you might want to use them for. But the thing is what happens if you put them on a board and you have a little bit of overvoltage problem or a little bit too much current goes through them? We've got a power supply here that's going to be supplying a lot of volts to these capacitors, and all it's just going to do, we're going to crank it to 36 volts, which is way beyond the voltage rating of these capacitors, and we're just going to see what happens. So first of all, we have a ceramic hooked up here, and I believe we are at 36 volts, and we're about to shock the crap out of this ceramic capacitor. You ready? 3, 2, 1. Not a whole lot. The next one we have in store is an electrolytic capacitor. Now these guys actually have a bunch of stuff stored in there. We'll go with the magic smoke. So if you see magic smoke, it's probably one of these going up. Let's figure out what happens. You ready? And now we have the tantalums, and you will see why these things are evil if you overvolt them. Here we go.
So it's not uncommon to actually burn out these little capacitors. The tantalum ones that he's talking about, they're a really big problem in the lab, because if something's going wrong in the circuit, then I'm assuming immediately that you just overvoltage the capacitor and burnt it out. And you can smell it. So the next thing that we want to look at is that I wanted to sort of like talk about applications. And I think that the applications are super fascinating. Now, I want to address capacitor questions. So what we just did here is that we just saw the video, and this was bust a cap. So if you go to the lecture links here, you'll see that the full video, it's worth seeing. It's about 4 minutes or something. He goes into some really interesting stuff about capacitors. So this was just to whet your appetite. So a common question, and a lot of people ask this question, by the way, why can't we use big capacitors instead of batteries? And I'm going to tell you, it's not a hard answer. And one of the things that you want to remember here is that there's a couple of reasons why. The first one I would say here is that capacitors are temporary they are temporary storage of energy. That is a big one right there. Okay? Because as soon as you use up the energy, you have to charge them back up. They don't magically recharge by themselves. But another one that's really important, but they cannot contain as much energy density as batteries. Okay, that's another big one right there, but they cannot contain as much energy density as batteries. Batteries have the ability to keep putting out energy, not capacitors. So because of these reasons, it makes them unusable or unsuitable, maybe is a better word, for long-term energy storage. Okay, you can't do long-term, and it's not continuous. Now, that being said, There are supercapacitors. And supercapacitors are pretty damn impressive. Like one of the really impressive ones, they have a supercapacitor from a company named Maxwell with, look at this number, 3,000 farads at 2.7 volts. By the way, you can purchase these guys. You can Google them, and they're about somewhere around $50 to $60. I mean, I can't believe this. Now, what's impressive about these guys is that you have to charge them up with a battery. But once you charge them up for a battery, these can store energy, a lot of energy, and release it slowly. That's the reason why you would want a battery bank if you have solar panels. But you should look at the fine details. Now, what I want to show you here is that I want to show you another video. It's short, so I've cut this down quite a bit. It's longer. It's also in the lecture note that's worth looking at. So let me go find this.
Capacitors are fully charged. Here I have a digital multimeter to measure the voltage. Okay, 4.97 volts, and each supercapacitor is 2.7 volts, and when you connect in series you will get 5.4 volts, and you will not any longer have 3000 farads, because you connect capacitors in series. The capacitance drops to 1500 farads. Okay. First I'm gonna hook up these small bulbs and see the voltage drop. Okay, 2 bulbs. And the voltage is steady, 4.97 volt. 6, alright. Now I'm gonna try to power these geared wheels. We are still at 4.96 volts. And the voltage is holding. This is great. Next experiment is to make a short and just to monitor the voltage. Please do not try this at home. I'm gonna short positive with negative pole of the supercapacitor, and believe me, this is not held for the supercapacitor, but I'm gonna try it. Whoa.